In these next couple videos, we're going to be checking out section 6.5, and that's the graphs of the other trig functions. In the last section we just did sine and cosine. Now we're going to wrap it up with tangent, cotan, and all the reciprocal trig functions. So we're going to sketch the graphs of the tangent functions. That'll be today in this video, and cotangent also. And then in the next video we'll talk about secant and cosecant, the reciprocals of sine and cosine. And we're going to be able to sketch the graphs of dampened trig function. We'll just talk about that a little bit at the end. Okay, so for the tangent graph, remember tangent is sine divided by cosine. And also we're going to look at this graphically here in the first quadrant of the unit circle. Remember, our x-coordinates are cosine values and our y-coordinates are sine values. So when we think about tangent as sine divided by cosine, that is sine here at the 0 radians, sine is 0 divided by 1. So our tangent value is going to be 0 divided by 1, or 0. So when we start thinking about the graph, here at the origin, we'll have an intercept. We plug in a 0, out comes a 0. We have a value at the origin. What happens when we get to a half pi radians? We're going to have sine 1 divided by cosine 0. Uh-oh. We can't do that. Remember, dividing by 0, either the world was going to blow up, or in the case of this, we're going to have an asymptote. So at a half pi radians, we're going to have a dotted line, an asymptote that our graph will approach but never achieve. And if we think about the fourth quarter of the unit circle, as we head down this way to negative a half pi radians, we're going to have the same scenario. Negative 1 divided by 0, or an asymptote. So here at negative a half pi, we're going to have another asymptote. And if we think about what happens not when we get to a half pi radians, but very, very close to a half pi radians. We might have an x value of 0.000001, something very, very small, and our y value would be something like 0.999999. And we're dividing a number, well, it's almost 1, divided by a very, very, very small number. We're going to be headed off toward infinity. So our tangent values, as we slide up the unit circle here, at pi over 4 radians, the tangent is 1, sine divided by cosine. But as we move up that next quarter radians of the unit circle, as we approach pi over 2 radians, we're going to head toward infinity. Positive infinity, but we have our asymptote, so we're never going to achieve it. So we're heading up to our asymptote. And on the third quadrant, we're going to have the same thing, but with negative values. As we head toward negative pi over 2 radians, we're going to head toward our next asymptote, and we're going to head down toward negative infinity. And we can see from this graph, what is the period of this function. Well, to complete a full cycle, that's just the distance between our asymptotes. From positive half pi to negative half pi, that is 1 pi, will be the period of the tangent, and we'll later see the cotangent function. And what we just did in that previous slide, here they have it in table form in the book. You're at an x value of 0, your tangent value is 0. At a quarter pi radians, it's 1. As you get closer to pi over 2 radians, you're getting bigger and bigger very quickly until you attain pi over 2, at which your value for tangent will be undefined. And the same holds true in the negative direction. So here's the graph of the basic tangent function. We already talked about it. It has a period of pi radians. The period is going to be split right down the y-axis. If we know what the period is, half of it will exist on the positive side of the y-axis. The other half will exist on the negative side of the on the left side of the y-axis. The domain is all real numbers except the numbers equal to pi over 2 plus some integer n times pi. That just shows where our asymptotes are going to fall. At plus or minus half pi and every pi radians after that. The range on the y-axis is from positive to negative infinity. Again, here's our asymptotes, and we're symmetric about the origin. Now when we sketch it, the book says here, to sketch the graph, y equals a tan of the quantity bx minus c. It's similar to sketching the graphs of sine, in that you locate key points and identify the intercepts and asymptotes. 2 consecutive vertical asymptotes can be found by solving these equations. We take what's in the parentheses after our tan function, bx minus c, and we set bx minus c equal to the left usual asymptote at negative a half pi, and we set the same bx minus c equal to the positive pi over 2 radians for our other asymptote. Another way to look at it is, once you know the period of the tangent function, here we know it's pi radians, and half of that will exist on the positive side of the x-axis, the other half will exist on the negative side of the x-axis. So you could just take the period pi, we know that tangent always has a period of pi, and if we divide it by the number in front of the x, the b value, we'll know how much the period is, and then we'll know that half of that period is on the positive x-axis, half on the negative axis. So the midpoint between two consecutive vertical asymptotes is an x-intercept of the graph. The period of the tangent function is the distance between two consecutive vertical asymptotes. The amplitude of the tangent function is not defined. After plotting the asymptotes and the x-intercept, plot a few additional points between the asymptotes and sketch a cycle. Finally, sketch one or two additional cycles, maybe one to the left and one to the right. So when we look at example 1 here, we're going to graph a tangent function, and what we have is y equals the tangent, and that is x over 2, or 1/2 x. Now when I graph these, just like we did with the sine and cosine, we want to find the period. In sine and cosine, we would divide 2 pi by the number in front of the x variable. But now that we're dealing with tangent, tangent only has a period of 1 pi. So the period of this function is going to be pi radians, the usual tangent period, divided by the 1/2, which is our b value. Pi divided by 1/2 is 2 pi. So we know the period of this function is 2 pi. And if we remember, we're symmetric about the y-axis, so if the period is 2 pi, I'm going to have half of that on each side of the y-axis. So if we cut 2 pi in half, it's going to be 1 pi and negative 1 pi. So there is one period of our tangent function. We know we're going to have an asymptote here at pi radians, and another asymptote here at negative pi radians, and we have an x-intercept at the origin. And the basic tangent graph, the positive tangent goes up to the right and down to the left. So there's one cycle of our y equals tangent of a half x. And if we look here, the distance between the asymptotes is our period, and we found that already right here. That's 2 pi. From asymptote to asymptote was 2 pi. Let's do our next cycle then. So if we go out another 2 pi, from 1 pi we add 2 pi to that, and we'll get 3 pi. And right in the middle there would be 2 pi. So our next asymptote occurs at 3 pi. We have an x-intercept between the asymptotes at 1 pi and 3 pi, right here at 2 pi. And we go up to the right and down to the left. And let's hop over and do one more on the negative side. Another period would be 2 pi. So from negative pi radians, that would take us to negative 3 pi, with negative 2 pi in the middle. Negative 3 pi will be our next asymptote. In between the asymptotes, we have a x-intercept at negative 2 pi. And because it's positive tangent, we go up to the right, down to the left. If that had happened to be a negative tangent, that just changes your arrows. Instead of going up to the right, down to the left, negative tangent would go up to the left and down to the right. Example 2, here we got one at negative 3 tan of 2x. So let's find the period. The period is pi divided by the number in front of x, our b value, and here it's a 2. So the period of this function is going to be a half pi, and half of that will exist on the positive x-axis, half on the negative x-axis. So if we cut half pi in half, we get a quarter pi. So here at positive and negative a quarter pi, we're going to have our first asymptotes. And right in between our asymptotes, we're going to have the origin, and we're going to have our x-intercept. And because this is negative tangent, we're going to go up to the left, down to the right. You know that 3 just makes it go up quicker. So, whereas the regular tangent graph might have a line that looks like this, the negative 3 tan is going to be a little steeper. It'll go up a little faster. So up to the left, down to the right for negative tangent. And our period here between asymptotes was a half pi. So let's go out another half pi. So if this is 1/4, half pi would be 2/4. Oops. Half pi. And then we're going to have 3/4. 1/4 plus 2/4 is 3/4. There's our next asymptote. And our x-intercept will be right in the middle, pi over 2, and up to the left, down to the right for negative tangent. And we could do the same thing in the negative direction. Here would be negative 3/4 pi. In the middle would be negative a half pi. And we have our asymptote at negative 3/4, x-intercept at negative pi over 2, up to the left, down to the right. Now the cotangent function is just the reciprocal of tangent. So cotan is cos divided by sine. So wherever our sine value is equal to 0, we're going to have an asymptote. If we just look at the x-axis here, where did sine values equal 0? Well, sine was 0 at the origin, and at pi radians, and at 2 pi radians, and every pi radians after that. So there is going to be the asymptotes of cotangent. And cotangent is the reciprocal, and you can also think about it as a reflection of the tan function. Whereas tangent usually crossed through the origin and went up to the right, down to the left, we've now been shifted to the right. All our asymptotes have been shifted over a half pi. And cotangent is sort of like negative tangent. It goes up to the left to approach its left asymptote, and it goes down to the right to approach its other asymptote toward the negative infinity side. The period is the same, 1 pi radians. The domain, the numbers that are valid on the x-axis that we can put in are all x values not equal to pi times some integer. 1 pi, 2 pi, 3 pi, 4 pi. Those are all where our asymptotes exist, therefore they're not part of our domain. The range on the y-axis, all values from positive to negative infinity, and it's also symmetric about the origin. So here let's take a look at the graph of 2 cotan of x over 3, or again I like to pull my fractions out. That's 2 cotangent of 1/3 x. So the period of tan and cotan is pi radians divided by the number in front of x. And here we have a 1/3. Well, pi divided by 1/3 is equal to 3 pi. So we know the period of this function is 3 pi, and that tells us where we can find our first asymptotes. For the basic cotangent function, the y-axis is an asymptote. So I'll just do a red dotted line over the y-axis to remind me that that is an asymptote. And now the period here is 3 pi. So our next asymptote will be at 3 pi. Now let me move that a little closer. We'll do more than one cycle here. So here's 3 pi, 6 pi, and let's go to negative 3 pi. And we know at these spots we have our vertical asymptotes. In between these asymptotes we'll have x-intercepts. So here would be 1.5 pi, or 3/2 pi, x-intercept. Right here at 4.5 pi. And at negative 1.5 pi will be x-intercepts. And remember, cotangent goes up to the left, down to the right, and that too will just make it go up a little bit quicker. So up to the left, down to the right, with the y-axis being one of our asymptotes. And there are 3 cycles of 2 cotan of 1/3 x. Here on the next slide and the one after it, there are 3 Huddle problems. And this last one here, we didn't really talk about that. This is the cotan of a shift. What that is going to do is just move all of our asymptotes pi over 2 radians to the plus side, to the right. So give those Huddle problems a shot. Pause the video, try the Huddle problems, and then start the video back up, and check out how you did. Okay, in the first one, we have negative 2 tan of 3x. The period of tangent is usually pi radians, but we divide by the number in front of x. That becomes pi over 3. So we know we have a period of 1/3 pi radians, and for the tangent, remember that's equally split around the y-axis. So a half of a third is a sixth, and to negative a sixth. There are our first two asymptotes. So I'll use some dotted lines for those. And we have a 2 value there. That just tells us we'll go up or down quicker. And it's negative. Tangent usually goes up to the right, down to the left, but that negative sort of mirrored it. We're going to go up to the left and down to the right. Down here in the next one, the tangent of x over 3, or the tangent of a third x. The period of tangent is pi divided by our b value, and here that's 1/3. Pi divided by a third is 3 pi. And tangent is, again, equally distributed. That period of 3 pi will be half on the positive side, half on the negative side of the y-axis. So here we're going to have out to 3/2 pi, or 1.5, and negative 3/2 pi will be our first two asymptotes. And because it's positive tangent, we cross at the x-axis of the origin, and we're up to the right, down to the left. And let's see, maybe we can squeeze another period in here. This is 1.5, so if we come out here to 4.5 pi radians, we're going to have another asymptote. Right, let's see what's in between. We have 1.5 and 4.5. The distance between them is 3. So if we had 3, or 1.5 to 3, 1.5 to 1 at 3 pi radians, we're going to have our x-intercept. Yeah, our first x-intercept was at the origin. Our next one will be 3 pi later, or 1 period later. And again, tangent will be positive tangent up to the right, down to the left. Last Huddle problem. This is the shift. So let's see what happens here. Well, first let's find the period. The period is pi divided by the number in front of x, and here it's just a 1. So we know we're going to have a period of pi radians. Now the last part here is the shift, and it's to the minus side. So we have a shift of a 1/2 pi to the right. Now let's think here, cotan. Cotan had an asymptote of the y-axis. Well, now that asymptote is going to be bumped over to pi over 2 radians. And then the period is pi after that. So we're going to have one asymptote at pi over 2 radians. And then pi later, at 1.5 or 3/2 pi radians, we'll have another asymptote. If our period is 1 pi and we have an asymptote here at a 1/2 pi positive, 1 pi later would be at negative a 1/2 pi. And then every pi radians after that. So here at negative 3/2. So cotangent usually has the y-axis as an asymptote. But because of this shift, our asymptotes all got shifted pi over 2 radians. So in between these asymptotes, we have our x-intercepts, one of them being at the origin. And because it's cotangent, we go up to the right and down to the left. Up to the left, down to the right, excuse me, for cotangent. Now this should look kind of familiar. It looks sort of like the tangent graph. The tangent graph goes through the origin and goes usually up to the right, down to the left. So what we have up here, our given function, we could say this is exactly the same as negative tan of x. If we just graphed this. If I said graph negative tangent of x, you'd graph those lines right on top of the ones that we already have. The homework for this section, we just have 6 problems, 7, 9, 20, 22, 23, 28.